The third slide puts the various pieces together to talk about the formation of the solar system. But before we do that, one other major piece of information comes from other places of star and planet formation in the galaxy. This is why the reading assignment included sections of Chapter 13 in Astronomy Notes. We look at other places where stars and planets are forming now to understand how our solar system formed 4.6 billion years ago. Processes now are the same as way back then. It's like you observing babies being born today to understand how it was like when you yourself was born. The Orion Nebula and the Eagle Nebula are two well-studied examples. The tiniest fingers or nodules sticking out of the so-called pillars of creation in the Eagle Nebula are several times larger than our entire solar system. Star and planet formation often occurs within a thick cocoon of dust that blocks our view, so we need to use infrared and millimeter radio waves, submillimeter radio waves, to peer through the dust. Longer wavelengths of light, that is infrared, microwave, and longer radio, can pass through the dust that blocks the visible, the optical, band of the electromagnetic spectrum. Also, forming stars and planets produce a lot of infrared light, so it makes sense to observe in the wavelength bands in which the objects produce most of their light. This picture contrasts the empty optical band view on the left with all the protostars detectable in the infrared on the right. In some cases, the dust has been cleared away, so we can see forming planetary systems in the optical band, or ordinary visible light. You can see dark dust disks in the mostly evaporated gas cocoons, and the Doppler shifts of various parts of the dust disks show they spin in a Keplerian manner, where the inner part spins much faster than the outer part, as you'd expect if the dust was made up of trillions of tiny bits. So in summary, there are three things we use to figure out the formation of our solar system 4.6 billion years ago. 1. The observations of primitive objects in our solar system, the asteroids, meteorites, and comets. 2. Observations of star and planet formation regions in which other planet systems are now forming around protostars. And 3. Computer simulations of gas, dust, and rock disks around protostars. A lot of back and forth of theory checked by many observations. The model that best explains the observed characteristics of the present-day solar system is called the Condensation Model. 4 basic stages are outlined in the picture. The solar system formed from a large gas nebula that had some dust grains in it from previous generations of stars. The nebula collapsed under its own gravity to form the sun and planets. What triggered that initial collapse is not known. 2 of the best candidates are a shock wave from a nearby supernova or from the passage through a spiral arm. A piece of the large cloud complex started to collapse about 5 billion years ago. As the piece, called the solar nebula, collapsed, its slight rotation increased to conserve angular momentum. In stage 2, centrifugal effects caused the outer parts of the nebula to flatten into a disk, while the core of the solar nebula formed the sun. The planets formed from material in the disk, and the sun was at the center of the disk. The solar nebula's composition was similar to the present-day sun's composition, about 93% hydrogen, 6% helium, and about 1% silicates and iron. And the density of the gas and dust increased toward the core where the proto-sun was. The inner, denser regions collapsed more quickly than the outer regions. When the solar nebula stopped collapsing, it began cooling, though the core forming the sun remained hot. This meant that the outer parts of the solar nebula cooled off more than the inner parts closer to the hot proto-sun. The only materials that could condense, or solidify, at the high temperatures close to the proto-sun were materials like rock and metals. Volatile materials, like water, methane, and ammonia, which made up a greater proportion of the solar nebula than the rock and metals, Those could condense or freeze out only in the outer parts of the solar nebula. In stage 3, the various types of solid particles collided with their neighbors and stuck together. Small eddies formed in the disk material, but since the gas and dust particles moved in almost parallel, nearly circular orbits, they collided at low velocities. Instead of bouncing off each other or smashing each other, they were able to stick together through electrostatic forces to form planetesimals. The larger planetesimals were able to attract other planetesimals through gravity and increase in size. This process is called accretion. More massive planetesimals had stronger gravity and could pull in more of the surrounding solar nebula material. Some planetesimals formed mini solar nebulae around them, which would later form the moons. The Jupiter and Saturn planetesimals had a lot of water ice mass, so they swept up a lot of the hydrogen and helium. The Uranus and Neptune planetesimals were smaller, so they swept up less hydrogen and helium, and there was also less around them to sweep up so far out. The inner planetesimals were too small to attract the abundant hydrogen and helium. In the fourth stage, at about 20 million or so years after the start of the cloud collapse, the protosun got hot and dense enough to undergo fusion and become a star. The sun turned on. The sun produced strong winds called T-Tari winds that swept out the rest of the nebula that was not already incorporated into the planets. The remaining planetesimals near the planets got swept up or flung out very far from the sun. The sun turned on about 4.6 billion years ago. The next picture explains in more detail why the terrestrial planets are small and near the sun, while the Jovian planets are large and far from the sun. At the rock-metal line, where the temperatures fell below about 1300 Kelvin, the rock and metal dust particles could clump to pebbles, to boulders, to planetesimals, to form the small terrestrial planets. At the frost line, or snow line, the temperatures fell below about 150 Kelvin, so the more abundant hydrogen compounds, water, ammonia, methane, etc., could form particles along with the rarer rock and metals that would clump to pebbles, to boulders, to planetesimals to form the cores of the Jovian planets. Because there were more ices than rock and metal, these Jovian cores could get large enough to suck up the nearby hydrogen and helium gas and get much larger very quickly to make the huge Jovian planets. This runaway accretion process happens for cores larger than about 7 to 10 Earth masses. So again, the planets continue to grow through accretion even after the sun turns on and clears out the gas of the solar nebula. The planetesimals close to Jupiter in the asteroid belt were too stirred up by the gravity of Jupiter to ever form a planet. In fact, Mars might have gotten larger if Jupiter hadn't formed so quickly. Icy planetesimals near Uranus and Neptune got flung out to form the Oort cloud, while those near Jupiter and Saturn were probably ejected entirely from the solar system. Now, the basic ideas described here have been confirmed, but there are details still to work out, as is typical in the process of science.